Hello, this is Mrs. Scarple, and in this video I'm going to go over imaginary and complex numbers. So we have previously worked with some quadratic equations where we ended up with solutions that had square roots of negative numbers. And we just went ahead and left them as the square root of the negative number. But in this video, we're going to use what Euler proposed, and that was that I be used to represent the square root of negative 1, and then to be included in what came to be known as the complex number system. So we've talked about real numbers in class, and real numbers include rational numbers and irrational numbers, and within the rational numbers we have integers and whole numbers and natural numbers. But now we're going to do overarching complex numbers. Complex numbers are going to be those made up of a real number with an imaginary number. So based on Euler's definition, we can identify what the value of I squared would be. So if you remember, when we take something like the square root of 2 and square it, that's going to be the square root of 2 times the square root of 2, which is ultimately the square root of 4, and the square root of 4 is 2. So when you square a square root, you're left with that value underneath the square root. So if we apply this to I squared is going to be the square root of negative 1 times the square root of negative 1, because I is the square root of negative 1. And using the logic that was used here, when you take a square root times itself, you're going to be left with the value underneath. So I squared is equal to negative 1. And that's going to be helpful for when we're simplifying expressions where we end up with an I squared. So now if we look at these problems, we can see how we can rewrite, like the square root of negative 2 can be written as the square root of 2 times the square root of negative 1, and as we use Euler's definition, the square root of negative 1 is I. I would also like to point out that you can see this written as I square root of 2. I know as I was going through my mathematics classes, I always saw the I in front of the square root. I never really saw it behind. And the same thing with the square root of negative 9. We can break that down to the square root of 9 times the square root of negative 1. 9 is a perfect square with its square root equal to 3. Rewrite that square root of negative 1 as 3i. Now I did have students ask in class, well, what if we just end up with the square root of negative 16? You can certainly, instead of having to rewrite it, you know the square root of 16 is 4, and because it is a negative, write it as 4i. So you don't need to do this intermediate step. So let's go through these examples, do some practicing with I squared before we move on to other operations involving what we call complex numbers. So keep in mind again, when something is squared, that means you're taking the item being squared times itself. So when we take the square root of 2 times the square root of 2, that's going to give us 2. I times I is I squared. And we defined on the previous slide that I squared is equal to negative 1, so 2 times negative 1 is negative 2. When we have 3i times 3i, that's going to equal 9i squared. And I squared again is negative 1, so we end up with negative 9, because 9 times negative 1 is negative 9. Now, operations with complex numbers use the same properties as real numbers. You're going to be combining the like terms. So when it comes to a complex number has a real part and an imaginary part. You'll add the real parts together and you'll add or subtract the imaginary parts together. You do need to be careful though when subtracting two complex numbers that you distribute the subtraction to both the real part and the imaginary part. So if we look at these examples, A is addition. You could essentially ignore the parentheses and just combine your like terms. So again, 13 and negative 12 are the real parts. 2i and minus 5i are the imaginary parts. So 13 plus negative 12 is negative 1, is positive 1, and 2i plus negative 5i is minus 3i. Again, you're just adding like terms. If we take a look at this next example, negative 7 and 3 are the real parts, 12i and that minus 6i are the imaginary parts. Negative 7 plus 3 is negative 4. 12i plus negative 6i is going to be a positive 6i. Now remember, I said with the subtraction, you need to make sure to distribute that subtraction to the real part and the imaginary part. So I recommend writing these without the parentheses, yet distributing that subtraction. So we end up with a minus 7 plus 3i. Now you can add the real parts and you can combine the imaginary parts. So 8 minus 7 is 1. Negative I plus 3i is plus 2i. So I'm going to do the same thing with D. I'm going to rewrite it, distributing the subtraction. And we have negative 9 plus 4i, subtract 9, minus or plus 4i again. So negative 9 subtract 9 is negative 18, and 4i plus 4i is going to be 8i. So again, negative 18 for the real parts plus 8i for the imaginary parts. So anytime you have a real part added or subtracted with an imaginary part, we call this a complex number. When multiplying complex numbers, we can use area models like we've been doing with binomials. And to make this look a little bit more like I would write it, I don't have as many cells. I have the 4 squares on the inside. 3 times 4 is 12. 3 times 2i is 6i. Negative 5i times 4 is negative 20i. Negative 5i times 2i is negative 10i squared. And then we can combine like terms. We can write it out. So we have the 12. 6i and the minus 20i are like terms. They combine to give us negative 14i. And we can write the negative 10i squared as negative 10 times negative 1, replacing that I squared with its equivalent value. That negative 10 times negative 1 simplifies to positive 10. We now have another real part that we can add to the 12 for 22 minus 14i. So when multiplying complex numbers is just like multiplying two binomials, such as x plus 5 times x minus 2. So let's take a look at some multiplication. I'm going to go ahead and draw an open area model. It does not matter which side which complex number goes. So I'm going to write 3 plus 2i on my vertical side and 5 plus 7i on my horizontal side. And then I multiply. 3 times 5 is 15. 3 times 7i is 21i. 2i times 5 is plus 10i. 2i times 7i is 14i squared. So we have the imaginary like terms, and we have the term with an I squared. So when I write this, I have 15. 10i plus 21i is plus 31i. And then that 14i squared I can write as plus 14 times negative 1. I can simplify the 14 times negative 1. So I have 15 plus 31i minus 14. Combine the real parts, 15 minus 14, and we have 1 plus 3i. Let's do the same thing with example B. Open area model. This time I'm going to write 10 minus 3a across the horizontal just to show you that it doesn't matter where or which side we write which complex number. So the 4 minus 6i went on my vertical side. Multiply. 4 times 10 is 40. 4 times negative 3i, negative 12i. Negative 6i times 10 is negative 60i. Negative 6i times negative 3i is a positive 18i squared. We have like terms, and we have the term with an I squared that we'll write different. So we have 40. Negative 60i plus negative 12i is negative 72i. And then we have positive 18 times negative 1. We can multiply that. So we have 40 minus 72i minus 18. Combine the real parts, and we have 22 minus 72i. Now we do have some special cases. If we look at these complex numbers, it's the same real part, the same imaginary part, but they have opposite signs on that second term. We call these conjugates. So when we multiply, and again I'm going to use an area model to do this, we're going to see something special happen when we multiply conjugates. 4 plus 2i, 4 minus 2i, and we've seen this pattern happen when we had difference of squares. 4 times 4 is 16. 4 times negative 2i is negative 8i. 2i times 4 is positive 8i. Positive 2i times negative 2i is negative 4i squared. If you look at these two terms here, they cancel each other out. So I'm left with 16 minus 4 times negative 1, replacing that I squared with negative 1. And we have 16 plus 4 equals 20. So we don't have an imaginary part here. We multiplied two complex numbers and we ended up with a real number. There's no imaginary part to it. Let's see if that holds for for this next example. Three plus 5i, 3 minus 5i, 3 times 3 is 9, 3 times negative 5i is negative 15i, 5i times 3 is positive 15i, 5i times negative 5i is negative 25i squared. Again, the imaginary parts cancel out, and we're left with 9 minus 25 times I squared is equal to negative 1. So we have 9 plus 25 equals 34. Again, our answer is just a real number. There's no imaginary part. Now we can write all real numbers as complex numbers. It would just be that we'd have 0i. Since we don't need 0i, because 0 times anything is 0, we just write 34. So what do you notice about the answers? The answers are real numbers. Because the imaginary parts cancel out. So that is a look at imaginary numbers, complex numbers, and the operations with complex numbers.